Hi everyone. So today we're going to be talking about exponential functions, how to graph them, what they look like, what they mean, what their equations look like. Before that, I was going to start with a little fun activity that kind of shows you exponential growth. You can certainly do this on your own, like while you're watching the video, or you can just listen. If you took a sheet of paper and you folded it in half, and then folded it in half again, and then folded it in half again, probably the most number of folds you could probably get is 7 if you're really strong. So you can certainly pause the video and try to fold the paper and see who can get the greatest number of folds. If you can get to 7, if you're strong enough to squeeze that paper and get to 7, the paper has gone from literally paper thin, we have that expression paper thin where it can cut you, to now at 7 folds, it's about the thickness of a notebook. Okay, so this is about the thickness of a notebook, your average notebook. If you were to continue folding that paper just 3 more times, if you got to 10, it would be about the width of your hand, including your thumb. If you were to be able to fold that paper just 2 more times, it would be about 1.5 feet tall, which is about the height of your average stool. If you were to continue folding 2 more times, it would be about 5.5 feet tall, which is about my height. Okay, the average, quote unquote, average person's height. At 17 folds, if you were to go 3 more folds, your paper would be as tall as a 2-story house. It would be 43 feet tall. If you were to just go 3 more folds from there to 20 folds, the paper would be the thickness of it would be 1,450 feet tall, which is the height of the Sears Tower. If you were to fold 10 more times from there, your paper would be the thickness of the height of the outer limits of the atmosphere. Okay, so this demonstrates exponential growth. The idea of exponential growth is if you're looking at the number of folds versus the thickness of your paper, you are seeing a graph that goes like this. It starts out very low, right, in thickness, and then quickly increases in thickness. As the value of x increases by 1, the value of y increases literally exponentially. Okay, so we'll take a longer look at that, a deeper look at this. So exponential growth functions, this is like your formula and what the graph looks like. The formula we use is y equals a times b to the x. A represents the y-intercept of your graph. We'll talk about b a little bit more, but b is 1 plus the growth rate, which we'll talk about more later on. You're in exponential growth, when something's growing exponentially, here it says b greater than 1. Your b value, this number here, will be greater than 1. Clearly it's 1 plus something, so it's going to be greater than 1. And the function is going to look like generally the curve that you see, where down by the x-axis over here, where I am putting some dots down there, it's getting ever closer and closer to the x-axis, but never actually touches it. It never gets to 0. Okay, and then it once it passes the y-intercept, it quickly rises. Okay, so we're going to learn to graph these. To graph these, we're going to be using always a table of values. So your table of values, I'm going to do 3 columns, 1 for x, on the right for y, and in the middle I'm going to do work. Okay, we're going to be using our negative exponents our knowledge of negative exponents and positive exponents to be able to evaluate these. We're not going to be using the calculator for this. It's actually faster and easier to do it without the calculator. Generally, I would pick x values from negative, that's supposed to be an inequality symbol, from -3 to +3. I would go from -3 to +3. Sometimes you won't be using the -3 and +3. They'll be too big or too small to graph. And then you might just use -2 to +2. But it's always a safer bet to just go -3, -2, -1, 0, 1, 2, 3. And then just start plugging in for x. Remember, it's your exponent. So 2 to the -3rd, if you think to yourself, that's the reciprocal of 2 to the 3rd, so that's 1/8. Okay, we'll graph these afterwards. Then 2, I'll switch colors so it's a little clearer. So then I'm going to do 2 to the -2nd. So that's the reciprocal of 2 squared, that's 1/4. And then I have 2 to the -1st, that's a half. And then remember 2 to the 0, anything to the 0 power is 1. And then I have 2 to the 1st, which is 2. And I have 2 squared, which is 4. And I have 2 to the 3rd, which is 8. Okay, so the fractions are those parts that we saw up here that were very, very close to the x-axis. So we just estimate. So I'm going to go -3, 1/8, it's like a little smidgen above the x-axis. -2, 1/4, a little smidgen higher. -1, 1/2, I'm going to be like right in the middle. 0, 1, 1, 2, 2, 4, and 3, 8. Okay, when you connect, it is not a line, it's a curve. So you make it look curved. And you freehand it as best as you can, making this part get closer and closer to the x-axis, and then going up, arrows in both directions, and then you label y equals 2 to the x power. Okay, it doesn't have to be the prettiest, it just needs to show that general shape. All right. Now, we talked about really quickly up here how a is the y-intercept, this number here. So when you look at y equals 2 to the x, think to yourself, well, what's the y-intercept? If you look at the graph, the y-intercept is over here, it's at 1. So if I were in class with you now, I would ask you, so where do we see the y-intercept in the equation? And that is that it's really y equals 1 times 2 to the x. So that's our y-intercept here. And the 2 is telling you that all the y values are doubling each time. So if you look at the y values on the table, 1/8 doubled is 1/4, 1/4 doubled is a half doubled is 1, 1 doubled is 2. So every time the y value is double, with every increase of 1 on the x, the y value is doubling. Okay, so here are some graphs that you could see all together that just shows you, like, as the b value, remember the 2 to the x, 3 to the x, 4, those are the b values. As the b value is increasing, it's showing you how the rate at which the y values is increasing is greater, and also that they all have the same y-intercept. They all go through 0, 1 because they all start with 1 times 2 to the x, and 1 times 3 to the x, and 1 times 4 to the x. Okay, so we're going to take a look at the next one. I'm going to set up a table, and again I'm going -3 to 3, -3, -2, -1, 0, 1, 2, 3. And I'm just going to plug in. So this is going to be 2 times 3 to the -3rd. So this one I'm going to have multiple steps. Remember, exponents first. So 3 to the -3rd is 1/27th. And 2 times 1/27th, remember 2 is 2 over 1, so that's just 2/27ths. That's just a really small decimal that's going to be really close to the x-axis. And I'm going to continue. So this is going to be 2 times 3 to the -2nd. So that's really 2 times 1/9, and that's 2/9. You could see this is actually faster than using your calculator, okay? 2 times 3 to the -1st is really 2 times 1/3. 2 times 1/3 is 2/3. And then 2 times 3 to the 0 is really just 2 times 1, which is 2. And then 2 times 3 to the 1st is just 2 times 3 is 6. And 2 times 3 squared is 2 times 9, which is 18. And 2 times 3 cubed is 2 times 27, which is 54. Okay, so you'll notice a couple things. One is I am definitely not going to be able to graph this one. I'm not even on this grid, depending on the grid that you get. I'm not even going to be able to graph this one. So I'm really just going to be graphing, a couple of these decimals. I'll start with -2 and 2/9, -1 and 2/3. I could probably go a little further for this one. 0, 2, my y-intercept is at 2. 1, 6, 1, 2, 3, 4, 5, 6. Sometimes I'll give you grids like on your homework that go up higher and that they'll have a scale, but this one doesn't. So that's all I can graph for this one. And I'm going to label, this is not very good on this program, y equals 2 times 3 to the x. All right, I'm going to stop this video and I'm going to do a new one because sometimes it doesn't play when it's too long. To be continued.